apply all of this to an exam, we're going to get the function fx 2x to the 5/3 plus 5x to the 2/3, and we want to see or to find the extrema in this interval, -8, 1. Okay, so first of all we have to find f prime, okay, and see where it is valid. Okay, so this is 10/3 x, and then this is -1, so this is x to the 2/3, and then we have plus 2/3 x to the -1/3, right? And now, well, this is okay. This is going to be continuous in the whole interval, but this is not going to be continuous at 0, right? At 0, this is not defined. Okay, so we can. This is valid for x different than 0. Okay, and then we have to. So the first step is to find the values that makes the derivative 0, and then check if they're local extrema. Then find the values where the derivative doesn't exist, so that's at 0. And then we need, in order to check if they're extrema, we need to compute the sign of the derivative on the left and not on the right. Okay, so for instance, for a maximum, you will have that the derivative on the left is positive and the derivative on the right is negative. Okay, so you need this, and for a minimum, you need the other way around. You need negative on the left and positive on the right. Okay, and then we have all the local extrema, and from that we can get the absolute extrema by comparing, right? Okay, so let's first compute the values that make this derivative 0. Well, we have said this is not valid at 0. Let's see what's the derivative at 0. We have the limit when x goes to 0 of this, right? F at x minus f at 0, which is 0 divided by x, and so this is the same as the limit when x goes to 0 of 2 to the x 2/3 plus 5 to the x of -1/3. And the problem is that this limit doesn't exist because how to say this, this is divergent. Okay, so it doesn't exist, so the function is not differentiable at 0. Okay, so first let's see what are those that make the derivative equal to 0, right? So let's see, we can rewrite the derivative as 10/3 times x plus 1 times x to the -1/3, right? So there's only one value of x that makes this equal to 0, which is f prime at -1, which is 0. Okay, now if x, we want to check if this is a maximum or minimum, right? So if x is smaller than -1, right, then we have that this is going to be negative, and this is also going to be negative, right? So the derivative is going to be positive. And then if x is smaller than -1, then this is negative again, close to it, right? This is negative, this is negative, and then this is going to be positive. So we have that f is going to be negative. Okay, so we have positive on the left and negative on the right. -1 is a maximum, okay, a local maximum. And then we have so that's for the values that make the derivative 0, right? Now we want to see what happens at 0, right? So f at 0 is, well, let's see, f at -1 is 3. Okay, you can compute it because this is -1 to the 5/3 is -1, so 2 times minus 1 minus 2 plus 5 is 3, right? F at 0 is 0 again, but what happens with f of x when x is smaller than 0? Sorry, the derivative on the left of the of this point x equals 0, then this is going to be positive, and then this is going to be negative, so this is negative. And the derivative when x is greater than 0 is going to be positive, because this and this are positive values. Okay, so we have negative, positive, and we know that there's a cusp here because 0 is not differentiable, so this is a minimum. Okay, so we have a minimum at 0, a maximum at minus 1. Okay, and now because we're checking the values, the extrema of the function at minus 8, sorry, and this at this closed interval, we need also to check the value of the function at minus 8. If you compute this, this is minus 44, and the value at 1 is 7, and we want to check the derivative at x, when x is greater than minus 8, well, around minus 8, right? It's going to be positive, okay, because again, this is negative and this is negative, and the derivative when x is smaller than 1 is going to be positive again, right? So we have that this thing is in the left extremum of the extreme of the interval, right? And then we have this point minus 44, and the derivative is positive here, right? At this point, and this here on the so this is going to be a minimum, right? And for f at 1, it's going to be this value 7, and again the derivative is positive on the left, so that means that this is going to be a maximum. Okay, and so let me see. So taking this all together, we have that f at minus 8 is minus 44, and we know it's a minimum. Okay, so we also need to check the values of the function at the stream. F at minus 1 is 3, and we know it's a maximum. F at 0 is 0, and we know it's a minimum. And f at 1 is 7, and we know it's a maximum. Okay, if you take all of this information and plot this function, okay, this is minus 8, this is 1, well, this is coming from negative here, and then there's a maximum here at 3, right? This is minus 1, this is 3, there's a 0 here, and there's a 7 here, something like that, okay, and something very small here. So what this is doing is the derivative is positive up until here, right? So the function is increasing, it gets to this maximum, and then the derivative is negative up until it reaches to 0. Now here it's not differentiable, so now after which the derivative is positive, so you have this. Okay, so with this information, this characterization of the function with the derivatives, we can get an idea of how the function behaves, right? And we can get this kind of not very precise drawing of the function, but a very qualitative behavior of the